Modeling discontinuous changes in momentum, delta functions. Suppose we want to model a situation where the momentum of an object changes very quickly. The flight of the golf ball is measured in seconds, but the momentum imparted to it by the club occurs over a period of milliseconds. In lots of situations, it makes sense to try to model this change of momentum as instantaneous, and the mathematical tool we will use to do this is called the delta function. To understand the delta function, let's start with some pulse functions. So P1 of t is 0 when t is less than 0. It's 1 between 0 and 1, and it's 0 when t is bigger than 1. So this is in some sense a unit push in that the area under our pulse function is 1. And so if you integrate the pulse function from 0 to infinity, you get 1, which is the area under the curve. P2 is very similar. The difference here is this function has height 2, but only is non-zero on the interval between 0 and 1/2. So the area under the curve is still 1, okay, but the pulse is now concentrated between 0 and 1/2. And when you integrate, you get 1 again. Okay, now Pn of t is a similar idea. This pulse has height n, but is only non-zero between 0 and 1 over n. So again, the area under the curve here is 1. And when we integrate Pn of t dt between 0 and infinity, we get 1. Now, it's pretty obvious the limit as n goes to infinity of Pn of t dt is 1 because every pulse function has area 1. So we could write the lim as n goes to infinity of Pn of t dt. And now what we're going to do is we're going to think of delta of t, which is the delta function, as in some sense the limit of this. What happens to our pulse functions as the interval on which they're non-zero shrinks to 0, but their height goes to infinity, but it does it in such a fashion that the area under the curve is always 1. Now, if we thought of delta as a function, it would be a very strange object. The area under the curve, when you integrate this thing, is 1. However, you think about its function values, the only place where there's a function value other than 0 is t equals 0. For t not equal to 0, we're 0, and as a result, but the height has to be infinite. Okay, so this thing right here is very strange in the sense of it's non-zero at a single point, and when you integrate it between 0 and infinity, you get 1. Now, this is not like any function we've ever seen, and it's not a standard function. It's called a generalized function. To understand some of the properties of delta, we need to look back at the pulse functions that this is in some sense the limit of. And Pn of t is just a standard function you can integrate. The integral of k times Pn of t is just going to be k times the integral of Pn of t dt, standard property of integrals. This integral is 1, so the whole mess is k. Since delta is the limit of this, the integral of k delta of t dt is also k, which means that if you have a constant times delta of t in the integral, the constant just factors out. Now, if we think about k delta t as a function, okay, it's 0 when t is not equal to 0, and it's infinite when t equals 0, which looked sort of like the definition of delta of t. But k delta of t is not delta of t. And this is essentially telling us that if we think about these things as functions, we're going to get in trouble. Delta functions make sense when you integrate them. If there's no integration involved, they don't. And since we're actually using these with Laplace transforms, which are integral transforms, delta is going to work. So let's take a look at some more properties of delta of t. Okay, so what is, for instance, the integral from 0 to infinity of f of t delta of t? So let's think about it this way. If we look at the pulse function Pn and let m be the minimum value of f of t on that interval, and let m be the maximum value, f of t Pn of t dt is going to be bigger than m Pn of t dt, because f of t is bigger than or equal to its minimum on that interval. This integral is m, because the area under Pn of t is 1. And now f of t Pn of t dt is going to be less than m, the maximum of f on the interval Pn of t dt. And that integral gives you m. And that means that little m is less than or equal to this integral is less than or equal to big M. And when we look at this interval, as n goes to infinity, it shrinks to 0. And both little m and big M, which are the maximum and the minimum of this thing on the interval 0, 1 over n, which is now shrinking to the point 0, both of these values have to go to f of 0, because that's the only thing they could go to if f is a continuous function. And when we look at this inequality, we see that f of 0 is less than or equal to the integral of f of t delta of t dt is less than or equal to f of 0, which means that this integral has to be f of 0. So if you integrate the delta function, delta of t, against a function f of t between 0 and infinity, what's going to come out is the function value of f at 0. Now, what about delta of t minus a when a is bigger than 0? Well, if we think about this thing, delta is concentrated at 0. So when t is 0, this thing turns on, and you get essentially unit area under the single point 0. This thing turns on, but it does not turn on at 0. It turns on when t is a, because then you'll have delta of 0. And the concentration of delta shifts from 0 to a. And what's going to happen is the area under the curve is still 1. Okay, and the curve is at this point the single point a. But now this thing turns on when t equals a, and it's going to pick out the function value not at 0, but at a, which is essentially what happens here. Because this thing turns on at 0, you pick out f of 0. Because this thing turns on at a, you pick out f of a. Now that allows us to actually compute the Laplace transform of delta of t minus a. So it's going to be, by definition, the integral from 0 to infinity of delta of t minus a times e to the minus st dt. And now remember what the rules are. This thing turns on at a and picks out the value of the function in the integral along with it at that point. And when t equals a, we get e to the minus sa. Okay, which is the Laplace transform of delta of t minus a. And when a is 0, you get the Laplace transform of delta of t, which is e to the minus 0, which is 1. So the Laplace transform of delta of t is 1. The Laplace transform of delta of t minus a is e to the minus sa. Now, another thing to notice. What is the integral from 1 to infinity of delta of t dt? Well, the answer is all the area under delta of t happens at t equals 0. That isn't in this interval. So delta of t is identically 0 on this interval, and this interval becomes 0. Okay, so delta t is concentrated at t equals 0. That's not in this interval. So you get 0 when you do this integral. But if we look at delta of t minus 2, now this thing will all be concentrated at 2, because when t equals 2, this thing turns on. The area under this thing is 1 at that single point. So if you integrate from 1 to infinity, here you're going to get 1. Delta of t minus 2 turns on inside this integral, so you get 1. Delta of t turns on outside this integral, so you get 0. Now, let's think about what we did previously, which is look at somebody hitting a golf ball. Okay, so let's suppose that our golfer hits the ball at t equals 4 and imparts an instantaneous momentum of k kilogram meters per second to the ball. How do we model this? And from ma equals f, we write mv dot, where v is the velocity of the ball, is equal to the force. And to get a discontinuous change in momentum, we're going to need an infinite force, and that infinite force is going to come from our delta function, okay? And it's going to be k times delta of t minus 4k, because that's how much momentum we want, and t minus 4 because that's when we want it to happen. And notice at t equals 0, the ball is sitting there, so v of 0 is 0. So we take this equation and we Laplace transform it. So the Laplace transform of mv dot is the Laplace transform of k times delta of t minus 4. Now, standard sort of stuff. This is going to be m times the Laplace transform of v dot, which is minus v0 plus s cap v. This is k times the Laplace transform of delta of t minus 4, which we saw was e to the minus 4s. Now, v of 0 is 0, and we'll have on this side m times s times v. So we will divide by s, and we get mv is k e to the minus 4s over s. And now we back transform. The inverse transform of little m times cap v is going to be k times the inverse transform of e to the minus 4s over s. And the inverse transform of cap v is little v. And the inverse transform of e to the minus 4s over s is the step function u4 of t. So we get mv is k times u4 of t, which tells us that mv is 0 when t is less than 4, and is k when t is greater than or equal to 4. So notice that we have, in fact, imparted a momentum of k to this golf ball at t equals 4. So that's the way we do this. If you want to impart momentum k, you use as your forcing function k times delta of t minus whenever you want to impart the momentum. The last example should illustrate that there is some sort of a connection between the delta function and the unit step function. As we were driving by a delta of t minus 4, and the thing that showed up in the answer was u4 of t. To understand this connection, we start with the integral from 0 to t of delta of u minus a du, which is in some sense an antiderivative for delta of t minus a. Sort of the fundamental theorem if you could actually trust delta to be a regular function. But now let's look at this integral. If t is less than a, the integral from 0 to t does not include a, delta never turns on, and we get 0. But if t is bigger than or equal to a is in this interval, delta turns on at a, and we get 1. So if t is less than a, we're getting 0. If t is bigger than or equal to a, we're getting 1. And that means this integral is the function 0 when t is less than a, 1 when t is greater than equal to a, and this is ua of t. So in some sense, ua of t is an antiderivative of delta of t minus a.